Hi everyone, thanks for your interest in the 2023 Open Catalyst Challenge. I'm Brandon Wood and my partner today is Mohammed Schwabi. We're going to be giving you an overview of the challenge, including the motivation, defining the task, the evaluation metric, the data that can be used, and finally covering a few of the ways that this year's challenge can be approached. This is the third iteration of the Open Catalyst Challenge, and the goal is to foster the development of accurate and fast ML or non-ML methods for catalyst discovery and design. Catalysts have a wide range of applications from renewable energy storage to agriculture. Our team is particularly focused on discovering catalysts for renewable energy storage through CO2 reduction or green hydrogen production. One of the difficulties with finding new catalysts is that the number of candidates is huge. It's far too large to test experimentally, so computational screening has begun to play a critical role in the design process. But how are catalysts actually screened? Well, an important quantity for screening catalysts is the adsorption energy, or how strongly a molecule, that you can see here on the left, referred to as the adsorbate, interacts with the catalyst surface. You don't want it to be too strong or too weak. We need to find that sweet spot where it's just right. The adsorption energy of reaction intermediates can actually be really powerful descriptors that correlate with experimental outcomes such as activity and selectivity. This is an example by Zhang et al., where they used CO and hydrogen adsorption energies to screen for CO2 reduction catalysts, and they actually found a good candidate that was experimentally promising. For activity on the left, you can see that you want a catalyst in kind of the yellow-orange region, which I put a box around. And for selectivity, you want something in the red. And they don't perfectly overlap, so there's some trade-offs to be made. But the important takeaway here is that these simple descriptor methods, utilizing adsorption energies, can be used to screen catalysts. One of the challenges of computing the adsorption energy is that it's a global optimization problem. And to illustrate that, here's an idealized energy surface of an adsorbate on a catalyst. We can add a few initial placements of the adsorbate on the surface. You can see those here indicated in orange and labeled 1, 2, and 3. Those are just different initial placements. Then we run relaxations to find local energy minimums. And this local optimization of taking an initial structure and predicting the relaxed energy, or IS2RE, was the task of our previous two open catalyst challenges. And you can approach this either with a direct, so you take the initial structure, directly predict the relaxed energy, or you can use a relaxation-based approach. And you can see the relaxation path indicated here with the dotted blue line leading to the relaxed structure. If you're unfamiliar with a relaxation, we start with an initial high energy structure. Then using DFT, atoms are allowed to move around until the forces they exert on each other are near zero. The final state is our relaxed or low energy structure. And for one catalysis system, this DFT relaxation takes around 24 hours on average. This year, we're interested in taking it a step further than local relaxations and actually finding the global minimum energy or the adsorption energy of an adsorbate surface combination. And the global minimum energy structure here is indicated with a star. So one of the things you might notice is that if we take a brute force approach to placing adsorbates, for finding the adsorption energy, it will require a lot of relaxations, which are expensive. One question we can ask to try and put some numbers to that is how many relaxations are needed to screen one material for CO2 reduction reaction. For one material, there's 90 surfaces. For CO2R, we look at 5 adsorbate descriptors. For each surface, there's 100 placements. And this ends up with about a total of 45,000 relaxations. If we were to use DFT to run those relaxations, it would take 120 CPU years, which is huge. And this is only for one material. We want to screen lots of materials. So this is where ML or other fast methods come in. We can significantly reduce the time it takes to run a relaxation from around 24 hours to on the order of seconds. Although I just mentioned relaxations, we're more broadly interested in kind of accelerating these absorption energy calculations to screen catalysts. And so you can do that by accelerating relaxations. You can also improve or reduce the number of initial configurations by using a better global optimization strategy or better initial guesses. So kind of with this goal in mind of accelerating absorption energy calculations, we formulated this year's task. Simply stated, the task is, given an adsorbate and a catalyst surface, compute the absorption energy. The metric we're going to use for evaluation of this year's challenge is success rate, and that's defined as the percentage of valid predicted absorption energies within 0.1 eV or lower of the DFT computed ground truth absorption energy. Now, the 0.1 eV threshold is used because that's roughly considered chemical accuracy. Okay, so we can walk through a couple examples. So let's say your prediction for the absorption energy is minus 3.15 eV, and the DFT ground truth absorption energy is minus 3.29. So the delta is more than the threshold of 0.1, so it's not considered a success. In another example, your prediction is minus 1.33. The DFT ground truth is minus 1.35. And in this case, the delta is 0.02, which is within the threshold and is considered a success. Now, if the delta ended up being 0.03 or 0.04, it's still considered a success. And the last example is if your prediction is actually below the DFT ground truth. And this is possible because we didn't explore everything with DFT, so it's possible that your model finds a better local minimum. And in this case, the delta, it's greater than the threshold, but it's lower than the DFT ground truth. So this is considered a success. This might leave you wondering, though, could your model just arbitrarily predict low energies? Then everything would be considered a success. Well, this is where we need to define what we mean by valid. So first, in order to be a valid prediction, the predicted energy needs to be within 0.01 eV of the DFT energy for the predicted structure. And so this is actually checking the local optimization is accurate on top of the global optimization. Essentially, so if this is the structure that you ran your prediction, your energy prediction on, we're going to take that exact same structure, run a DFT single point on it, and then check that your predicted energy is within 0.01 eV of that DFT single point. If it is, then it's considered valid. A second requirement to be considered valid is that none of the physical constraints of an absorption energy calculation are broken. So first is desorption. If the adsorbate is desorbed from the surface, it's no longer the absorption energy that we care about. Then we have dissociation, where an adsorbate actually breaks apart. And in this case, you have two adsorbates on the surface. And this, again, is not the absorption energy that we're looking for of the original adsorbate. Third, we have a surface mismatch. So this is when, during relaxation, maybe the surface reorganizes and would result in the energy referencing scheme no longer being valid. Okay, moving on to what data can be used for the challenge. We're going to be focused on the Open Catalyst 2020 dataset, which was generated a few years back now. At the time, it was the largest and most diverse Catalyst dataset to date, with around 1.3 million DFT relaxations, which relates to about 130 million training examples. And this required a lot of compute. In addition to the dataset, we defined tasks, released baseline models, and started a community challenge. So OC20 has multiple subsplits, and these are based on the task. So the first that I'm going to talk about is structure to energy and forces. So you take a structure, predict the energy and forces of that structure. The OC20 S2EF data has initial structures, intermediate structures along the trajectory, and the relaxed structure, in addition to the energy and force labels. So a second subsplit or second task is the initial structure to relaxed energy, or initial structure to relaxed structure. And in this data, we have just the initial structure, the relaxed structure, and the relaxed energy label. Finally, we have OC20 dense. And this is where there are about 85 different initial adsorbate placements per surface. So this really allows us to focus on adsorption energy calculation, or kind of finding that global minimum energy. So this differs from the original OC20, because in the original OC20 there was only one initial adsorbate placement per surface. So this dense data set really allows us to focus on computing adsorption energies. For this year's challenge, in terms of S2EF data, we're going to permit the 2 million split. So this is about 2 million individual frames. And the reason that we limit that from the entire data set is just to make the challenge more computationally feasible. So in addition, we're going to allow the IS2RE and IS2RS data, which has about 460K initial structures and relaxed structures. And then new this year is the OC20 dense data, and this we're going to use the in distribution split. So this has about 244 systems that are densely sampled. That results in about 15K initial structures and about 3 million individual frames. For the challenge test set this year, we're going to have 200 adsorbate surface combinations. So you'll need to make predictions on 200 systems. For each system, we're going to release 100 initial placements, and you're not constrained to these placements, but it's a place to get started. Additionally, we're going to be releasing ML relaxed structures, and so for the 200 combinations times 100 placements, there'll be about 20,000 initial structures, and we're going to take a few of our top models, run ML relaxations, and release those relaxed structures. Mohammed's going to be talking more about how those can be utilized in a few slides. So with that, I'm going to pass it to Mohammed to talk about ways to innovate.
What I want to talk about now is how to really approach this problem. Specifically, I want to highlight 4 different strategies that you can use to tackle this challenge. And of course, while you're not limited to this, I really want to get the ball rolling and get you thinking about different ways to approach this problem that you may not have thought about in the past years or in the previous challenges. Specifically, the first being improving ML potentials or building better models. And this is really what we've been commonly used to and been doing in the past. Second is fine-tuning or transfer learning strategies. Here is how do we leverage our existing data set along with the new data set to kind of improve this performance. Third is global optimization strategies. This is no surprise. This is a global optimization problem. While we've been doing things in a brute force nature, there may be more clever or systematic ways to approach this problem. And lastly is, how do you come up with better initial placements? While we have our method that we'll talk about later on, there could be more clever ways to place adsorbates on the surface or place them in better configurations that could lead to improved performance. And first, I want to start off with what we believe is probably the lowest barrier to entry for people with limited compute. We understand that people come from a wide range of backgrounds. Some may have more or less compute than others. And what we're trying to do here is really level the playing field as far as giving opportunities for everyone to compete, whether it be making it easier by providing relaxed ML, relaxed structures, or providing different ways to innovate. And what I want to highlight here is one way we think that could bring people with limited compute into the field. And that is kind of leveraging a structure to energy model. Here, we are leveraging the released ML relaxed structures that we will be providing. So what I mean here is, for a set of data, so we will be releasing initial configurations. Rather than requiring people to take ML potentials and run them to get ML relaxed structures, we'll do that ahead of time. We will take our kind of top 3 ML models, trained on of course, the limited 2 million data set, and get the ML relaxed structures. We will release those. All of those are currently publicly accessible for the validation set, and we'll be doing the same for the test set as well. Now, what you'll be doing here now is taking your ML potential and making more accurate energy predictions than the ML relaxed structures. So while we used our pre-trained ML models to get the ML relaxed structures and they have an energy associated with them, you may build an ML model or ML potential that is more accurate at making energy predictions. And so you'll take the relaxed ML relaxed structures, feed them into your ML potential, make energy predictions across all configurations, take the minimum across those configurations and those energies, and then you have your absorption energy and the structure associated with that absorption energy. Now, practically speaking, or on a closer look as far as implementation is concerned, how this will look like from a training and validation perspective is, one, you may be training on S2EF data. Specifically, you'll be focusing on energy here, but most of our S2EF data contains both energies and forces. So the data that you may be limited here to is OC20 S2EF 2 million and the dense in-domain data set. All this data is linked on the challenge website, so you can go check them out to download that specifically. And of course, for validation, we'll have the OC20 dense out-of-domain data set carved out for you to validate on. And specifically, we will kind of package this into an LMDB format. So we'll put the ML relaxed structures into an LMDB. This is for GemNet OC, ESCN, and SCN trained on 2 million. You will feed that into your ML potential, make energy predictions. If you're using our code base, these predictions will be saved out automatically in an NPZ file. If not, you'll just need to organize it in a similar manner. We have released a sample NPZ file that you can use and look at to make those predictions, or to provide a similar file. And then we have released an evaluation script where, given your NPZ file of predictions, we will evaluate it and spit out the success rate associated with your approach. Now, the reason we can actually evaluate this, and this goes back to the point Brandon made earlier, is that for a system to be valid and be considered successful, you not only have to have an ML energy that is lower than the ground truth DFT absorption energy or close, you also need to be, if you were to take a DFT calculation of your structure and compare that to the energy prediction from your model, they need to be within 0.1 EV. And the reason that is, as we mentioned earlier, is otherwise you could game the success rate by having a model that predicts negative infinity, and then you're always lower than DFT and you're successful all the time. So by requiring your model to also predict an energy that is similar to what the DFT energy of that structure would be, kind of really constrains that problem. And because a DFT evaluation is involved, we will have done that ahead of time. Because we are releasing the ML relaxed structures, we have computed the DFT energies ahead of time, and as part of the release for these relaxed structures, we'll also release the DFT energies so that the evaluation script can make use of that and give you an accurate success rate. Now, the big question here is how much potential is there in that approach? It seems very simplistic in the sense of we've taken the pre-trained models, we've run the relaxations, we've come up with the ML relaxed structures. And surprisingly, there's quite a large margin. And what we're looking at here is with the 2 million models, the models I just talked about, if you were to take the ML model on those initial configurations, get the ML relaxed structures, and of course you have the energies as well. If you were to just use those energies, you are looking at a success rate of around 30 to 40%. And of course, that's not great. And this is really the floor for this approach in the sense of if you were to just use the models we've released as is, you're around 30 to 40% with the 2 million models. Now, the question is, what's the ceiling associated with these structures? And really that comes to is if instead I had a more accurate energy prediction of that ML relaxed structure, and to do that, I can do a DFT calculation. So I can take my ML relaxed structures, do DFT calculations on all those relaxed structures, just a single point calculation, and I get that energy value. And if I were to use those energy values to compute the success rate, I am looking at around 70 to 85% success rate. So to emphasize is these are the same relaxed structures. These are the same ML predicted relaxed structures. And the only difference between the floor and the ceiling is the floor used the same ML model's energy prediction, but the ceiling used the DFT energy of that associated structure. And we can see that simply by improving energy predictions of these models, we can boost our success rate 30 to 40% to get us to that ceiling. And that's really what we want to see. And this is a huge gain from really existing pre-trained models that still have a lot of potential. Now, the question here is probably, okay, 70 to 85% is great, but what if I'm really trying to secure my position or to really win this competition? And you may think that, okay, maybe I need better ML relaxed structures. And if I want to go beyond 70, 85%, that's what it comes down to. And that's coming up with better relaxed structures than the ones the pre-trained models were trained on. And this workflow kind of looks really similar in the sense of that you start with a set of initial configurations, but instead of using ML relaxed structures that we released from our 3 top models on the 2 million dataset, is you may have your own ML potential that makes energy and force predictions. You come up with relaxed ML relaxed structures, and then you do the same thing. You make energy predictions across all those ML relaxed structures. You take the minima across that set. So you now have your absorption energy, and you also have the structure associated with that absorption energy. And that's what's really fed into evaluation. Now, the challenge here is we don't have a way to validate this approach during this initial phase. During development, there's no way for you to actually validate whether this approach is going to outperform what you had before. And the reason that is because I talked about how validation requires a DFT calculation and you to be within that 0.1 EV. And because we were able to do that before because we were releasing the ML relaxed structures. So we just did the DFT calculation ahead of time, and we know that it's the same structure that you'll be using. But here, your model may come up with different relaxed structures, and there's no way for you to actually, unless you have DFT to actually validate this on your end, we don't offer a way for you to actually validate this to come up with an accurate success rate. But despite that, I do want to point out that kind of the valid success rate tracks S2EF metrics very closely, such that if you come up with an ML potential that has S2EF metrics, specifically say energy MAE and force MAE, that is outperforming our baseline 2 million models, then it is highly likely that your approach, when applied to the same framework, will outperform our baseline 2 million models. So while there's not an exact way to kind of compute, a direct way to compute success rates, we kind of do have this proxy for success rate for you to track those S2EF metrics. Next is kind of leveraging this additional data set. I talk about how we will be releasing the OC20 dense in-domain data set for use. And how we actually use that to improve models has yet to be explored, and there is a large opportunity there for improvement. And kind of the very traditional way to approach this problem is take these 2 million OC20 2 million data set, train on that model, and just run this framework with that. Kind of one of the next very naive approaches is just combine the two data sets. So you just take the OC20 2 million plus the dense in domain, train on both of them, and then run this pipeline that we talked about earlier. Now, the one challenge kind of in this lower left-hand corner is this may require more compute than some people may have. So OC20 we're limiting to the 2 million, and the dense in domain is approximately 3 million data points. So together that's around 5 million data points, which may be a significant amount to train on. One thing I want to note here is this is where maybe fine-tuning strategies may help in the sense of rather than training everything from scratch on the entire data set, you can leverage our pre-trained models. So we have released all the top 3, all our models are publicly released, but specifically the 2 million pre-trained checkpoints are available. You can download those. Those have already been trained on OC20, so they are the best we've got them to be. You can freeze portions of those model weights and really fine-tune the rest, kind of update some of the parameters by using this new data set. Or you can kind of mix and match these different strategies to think of ways to leverage this OC20 dense data set and improve overall performance. Now, one thing I want to note here is for the released ML relaxed structures that I talked about on the previous slides, those will have come from models trained on only OC20 2 million. So I guess one very straightforward way to improve is training on the combination or fine-tuning on both data sets, or finding some way to leverage that additional data may or may not help you improve this task. Next, I want to highlight another strategy that's quite common in the computational catalysis field, and that's global optimization. And we talked about how absorption energy or finding the absorption energy is ultimately a global optimization problem. You have different minima, but what we really care about is that global minima. Now, how we've approached this problem is very, very brute force, and a lot of the community has historically done brute force approaches, but the innovation here is how do we come up with more systematic approaches? So in the brute force nature, we're just taking 100 different possible configurations of an adsorbate on a surface and then running with our ML potentials on all of those to find the minima. Now, one approach to innovate here is making use of more systematic strategies. And we've seen this in community more recently, and that's coming up with global optimization techniques such as minima hopping or simulated annealing. A lot of these approaches or algorithms have existed for tens of years that people are just now starting to explore in the context of finding absorption energy. And a lot of that is some of this is computationally expensive, but rather than doing it with GFT, you can kind of think of making use of these pre-trained models for these different approaches. So rather than brute force with an ML potential, you can use a global optimization strategy with these ML potentials to find better minima. And to highlight kind of the importance of this is really how do we come up with more interesting configurations that we wouldn't have been able to come up with just based off randomly placing adsorbates on a surface. And the work of Reuter here shown on the left-hand side quite recently is they come up with they use a global optimization strategy where they outperform a lot of existing work from the literature that did do a brute force approach. So their work here in red versus work they were comparing against in blue is that you can see that they're finding better minima than what was found in the literature at the time. One thing we've done recently is we've taken some of these systems and tried it with our approach. And while we're able to get the minima, a lot of the minima that this work has shown, we did miss a few minima in the sense of they came up with configurations that our heuristic or random strategy of placing adsorbates on a surface was not able to do better on. So this is certainly an opportunity for people to explore in the context of this challenge. And the big appeal here is it doesn't necessarily require training new models. And the reason I say that is a lot of this is very algorithmic or very different and a different application to how we've approached it. So our ML potentials are very accurate, and we've seen them do very well on finding absorption energy in a brute force nature. The natural extension is just continuing to use those pre-trained models and applying it to these more systematic strategies or these different global optimization algorithms that could find you better minima than what we've been doing in the past. And lastly, coming up with better initial configurations. I talked about how for both the validation set and the test set, for a given adsorbate catalyst combination, we will enumerate 100 different initial configurations on that surface. And this will be done via our heuristic and random kind of input generation code. All of this is publicly accessible. You can take a look exactly at the details of what's happening behind the scenes of how we're placing these adsorbates on the surface. But what I want to highlight here is we've picked 100 because that's what we've done in the AbsorbML paper. We've seen that to be a sweet spot. If we sample more placements on that surface, we don't see a huge improvement in success rate. So we've done something similar here for the test data set as well, excuse me. Now, the point here is you may come up with a strategy that you have a better way to place adsorbates on that surface. Rather than doing 100 initial configurations, maybe you have 20 configurations that are more accurate or more carefully crafted than the approach we're doing here. Of course, you may not be able to carefully kind of hand tune it for the entire 200, but maybe you have an algorithm that has a better way to place adsorbates on that surface. And really, we're allowing participants to freely generate other or more initial configurations. So you can generate 500 initial configurations if you think it's useful in your context. In our experience, we haven't seen a huge improvement, but we'd love to see strategies that maybe do benefit from sampling more, or maybe even sampling less, that you have a better strategy, or you just have a general different algorithm to doing so that can outperform what we've been doing in the past. And of course, a lot of these ways to innovate kind of aren't necessarily independent. Of course, you can combine using better initial placements with the strategies I talked about with maybe global optimization, or actually, I guess not global optimization, but maybe fine tuning or leveraging the S2EF better ML relaxed structures. These are really mix and match. This is really just to give you an idea of the potential degrees of freedom or ways to explore this problem. And of course, you aren't limited to these 4 different ways to innovate. I just wanted to highlight ones that came to our mind, or that we've seen in the community quite commonly, that we haven't explored in the context of finding adsorption energies for OC20 or at the dataset scale that we've been dealing with. And we'd love to see people explore these other avenues. And specifically, we want to make it accessible for people with varying access to compute. Some people may have more or less, and a lot of these strategies, you can find your niche depending on the compute available. If you can't train models from scratch, you can use existing pre-trained models applied to better initial configurations or better global optimization strategies. We're really trying to make it as accessible as possible for people with really the spectrum of compute. How do you get started? Of course, you're already here, so I'm glad you found this. And of course, all the details, all the links are provided on our challenge website. So that's opencatalystproject.org/challenge. All the links are available here. You can refer to the AbsorbML code base for all the utility scripts, for all the details of how to kind of detect unphysical structures or invalid structures. You can look at how we're doing the evaluation. The evaluation scripts will live there for the test challenge. Of course, the OCP repo is where we host our models, is where we host the OC20 dataset. As a reminder, that's where you can download the OC20 datasets. So for this challenge, you'll be limited to the S2EF 2 million and the dense in-domain dataset. Of course, you're also allowed to use the IS2RE dataset. All the details are on the challenge website, so just make sure to check there for the complete set of rules and restrictions. One last point I want to emphasize on or highlight is how much compute is actually required to compete. And this is really oftentimes a deal breaker for people, whether to compete in a challenge or not, just because they may or may not have the compute necessary to be competitive with other teams. And what I want to do now is really kind of emphasize the point that you don't need tens of thousands of GPUs to actually compete in this. There is a large spectrum of different ways to innovate or different ways to approach this problem, as I mentioned earlier. But just to give you some context of what it may take to train, say, 2 million S2EF data points or train an IS2RE data set, I just wanted to share this kind of table that we'll also have on our website of a breakdown of what we've seen using our models on our code base on our data. So we're looking at, say, for training S2EF 2 million, some of our top models require order thousands of GPU hours, upwards to 3,000 in some of our slower models like SCN. On the other hand, using IS2RE Direct, just trained on the 460,000 data points, requires around 75 GPU hours. And one thing I want to mention here is all these pre-trained models are publicly accessible. So just because you don't think you're able to build a brand new model from scratch prevents you from competing in this challenge, that isn't necessarily the case. You can take these pre-trained models, you can fine-tune them, you can do whatever else you can come up with, leveraging the models that we've already trained on our end, and we've put the compute in to kind of get these models. So just to give you some context of this is what it may take to train something absolutely from scratch on the left-hand side. Now, a lot of the strategies I talked about, or a lot of the ways to innovate, involve just running inference. So using these pre-trained models with a global optimization strategy, using them with different initial configurations, and a wide kind of different combinations of that requires just running inference or just using them for different strategies. And we kind of break this up into two components. So if I was interested in taking 20,000 initial configurations and running just ML relaxations from those, you're looking around between 45 to 500 GPU hours just of inference to run full ML relaxations on 20,000 initial structures. Now, of course, 20,000 isn't the number you may converge on. You may identify a much smaller set of initial configurations. You may run more initial configurations and require more ML relaxations. So that's really on the extreme end of if I were to run full ML relaxations with these models, that's the amount of compute we're looking at, which is certainly doable 1 or 2 days or 3 days for some of our top models for full ML relaxations. But the first approach we talked about, where your model doesn't have to run the relaxations, you just leverage the released ML relaxed structures, and your model is only making energy predictions on those relaxed structures. And the idea there is you are just making one forward pass to the model to make that prediction. And what we're looking at here is a lot less GPU hours. So here we're looking at 1 to 3 to 4, less than 5 GPU hours to actually make those calls. And we saw there that the opportunity for improvement is huge. To go from 30 to 40% upwards to 70 to 80% is a large range for kind of a large range to improve these models with as little compute as possible. So that is something to think about as far as how inference is concerned. I will leave, people can check this out, but just to give you a sense in this, in that you don't need hundreds of GPUs to actually compete in this. There is a niche for you, or there is a different way to apply this, compete in this challenge based off the different ways to innovate. So if you are really interested or really excited about this problem, definitely check out some of the different ways to innovate as far as what may be the easiest for you to participate. To highlight some of the dates that we talked about, of course, the competition has been announced. You're here checking it all out. The test data set will be released sometime in September. Between now and September, the validation data set, the released ML relaxed structures are available. Evaluation scripts exist. You can go ahead and start iterating, go ahead and start practicing, go ahead and start testing your approaches between now and September. Whatever you kind of come up with in the meantime, by then in September, we'll release the challenge test data set. So those are, just as a reminder, that is 200 systems. We'll release approximately 100 initial configurations per system. And for that total 20,000 initial configurations, we'll release the ML relaxed structures for our top 3 2 million trained models. So sometime in September, we'll release that data. You can, whatever algorithm or whatever model or approach you come up between now and then, you can apply it to that test data set, make submissions, and we'll have a means. We'll upload details as far as how to actually submit your energy and structure predictions. The deadline will be sometime in October, and of course, the winners will be announced end of October, and the winners will be invited to present their work at the AI for Science workshop at NeurIPS this year. And with that, just to leave some additional resources that we'll also leave in the description below, the challenge website, the AbsorbML paper, and we will be hosting weekly office hours between now and really the last day to make submissions for the challenge. And these will be held Wednesday 9 a.m. to 10 a.m. Pacific time, and Thursdays 4 to 5 p.m. Pacific time. We try to spread out the hours just so we can capture as many people as possible. Of course, we have the discussion board where you can leave any questions or comments or concerns, or if you think an approach is or isn't allowed, make sure to just comment there and ask us ahead of time just to be extra safe. Our GitHub, you can raise any questions or concerns you may have as far as the code details. And of course, our emails are provided here if you want to reach out and ask us any questions or have something specific to comment or you want to discuss.